Okay, I think we're all set. So hello, everyone. So welcome to this DIGA webinar series. Welcome back, I should say. So we've been out for a couple of months, but now we're back. So hopefully, yeah, we'll see how far we go. But for another couple of months, for sure, we will have some more interesting presentations. So today we actually have two presenters talking about learning for crowdsourcing, so also related to network processing. So we have Panos Panayotis Draganitis and Georgios Giannakis. Panos got his diploma at the National Technical University of Athens. Then he did his master's and PhD at the University of Minnesota, actually under the supervision of Professor Giannakis. And then very recently in the summer, he joined Michigan State University, working on data science, crowdsourcing, statistical signal processing, and so on. Professor Giannakis, of course, many of you probably know him, so he doesn't need a lot of introduction. So actually also got his diploma at the same university in Greece. And then he got his master's and PhD at the University of Southern California, then moved to University of Virginia, and then since 99 also since 99 at the University of Minnesota, where he then supervised Panos. He had different positions there at the University of Minnesota. The most prestigious is probably the University of Minnesota Presidential Chair in ECE. That was he has that position since 2016. Working on many different topics. Started in statistical signal processing, then kind of pioneered the field of signal processing for communications and networking, and then moved also to data science, IoT, power networks even, so very broad expertise. So we're very happy that he accepted our invitation to give a presentation here. Received also numerous awards, paper awards, personal awards. Maybe the most prestigious is the IEEE Fourier Technical Field Award in 2015. So very happy to have them here, and I think crowdsourcing is maybe kind of a new topic for many of us. So this is very interesting to hear about that. So go ahead, guys. Thanks.
Thank you, Gert, and thank everyone from the organizing committee for the invitation. Indeed, I supervised Panos, but in this particular subject and this particular presentation, Panos supervised me. So credit where is due. This is primarily Panos' name should appear first. And I would like to acknowledge his contributions in this field and teaching me. And as usual, advisors, when they get senior, they get the easier part of the presentation. So the outline of our talk, will start with some motivation that I will try to sketch for crowdsourcing and put crowdsourcing in context, historically, where it started from and where it is going on in the era of machine learning and AI and graph signal processing. So the G in DEGAS stands for graph, and Panos is going to start describing crowdsourcing of graph data and also a recent topic, the crowdsourcing under adversarial attack before conclusion. So as I said, it was back in 1906 that this parable of the ox was discussed in a farmer's market, where a seller was trying to invite people to buy lottery tickets, and the winner who would guess the weight of an ox lively presented there would get the ox, right? And 487 people guessed the weight of the ox. And surprisingly, Sir Francis Galton figured out that the smart way is to just take the average, right? And it turns out that the average, which was 1,197 pounds, came extremely close to the true weight of the ox. Now, fast forward more than 100 years later, still people recognize in this popular TV show that the most valuable help to get is to ask the audience when you get in tough spots and you don't know something. So the basic motivating question for this talk is it possible to harness the wisdom of crowds in a principled way? And that's what people like to call crowdsourcing. Okay. Now, let me say also, on the technical side, that one has to recognize the differences between fusing data, as, for example, in a modern automobile, you have laser and radar and cameras, and you are fusing heterogeneous data, but also you may decide to fuse decisions. And this was well known some years ago under the name of centralized inference at the fusion center. So suppose that you have sensors with limited resources in bandwidth and power, and instead of sending raw data, they prefer to send the label that this is, close to having an accident, or this is a pedestrian in an automatic car, in an autonomous driving vehicle. So that would be centralized inference, and pioneering work was done by Ziziklis in the late 80s. But the question to ask is, what does this sensor network-based inference with limited resources has to do with the modern era of machine learning and artificial intelligence? And the viewpoint most people are familiar with is that we're getting data feature vector sets that represent a cat or a dog or a gecko, and then someone gives us some labels, and we use this input-output data to learn or train a model that can be a neural network. And based on this model, new data come afterwards. And you can, if you have an X star, a testing image, then you can get whether the label of it, right? So that's the typical supervised case. But nowadays, people recognize that many tasks involve no labels, or maybe noisy labels, or very few labels. And there are so many names. The last one, or very few labels, goes under the name of semi-supervised learning, okay? So this is where crowdsourcing comes into picture. And in fact, you can view crowdsourcing as a broad class of weak supervision. And the people who provide noisy labels can be thought of as generic, possibly unreliable learning models. So suppose that you, instead of a huge neural network, you have smaller networks that will act like annotators that will provide possibly noisy labels. So from now on, I want us to think, we're going to talk about annotators, but you can think of an annotator as a less reliable, perhaps, learning paradigm model, okay? So I'll use that interchangeably. First, though, I want to ask myself, what are the challenges associated with crowdsourcing and when we should use crowdsourcing? First, as I said, the individual annotators may not be reliable or may even be adversarial. So that's a challenge for crowdsourcing. And the responses we have per annotator are sparse. So we don't have too many labels across annotators. And the impact, though, can be huge. If you have a successful crowdsourcing algorithm, then you can bypass the need for expert supervision. And that can buy you low-cost, efficient training of large-scale neural networks. So documented merits have emerged in a number of applications. I'll pick up 3, 4. On the left, what we see here, what I show here is the ground truth of liver image. And this is what a bunch of annotators found using crowdsourcing. And if you compare these two, you see they're very close. They marked the boundaries of this image. In contrast, look at the different annotator responses. they don't look too close to the ground truth. Nevertheless, judicious combining of their decision can create the crowdsourcing result that can be very attractive. And other applications appear in 6G, but also in general area of crowdsourcing, where the ways, for example, that is depicted here, includes a lot of drivers helping one another in identifying optimal routes or speed traps. And citizen science is another area where people are trying to figure out, for example, in the Galaxy Zoo, what is the smoothness or the rounded shape of a galaxy. But coming back to deep neural networks, they cry sometimes, the more complicated they are, the more they cry for labels. So if we can provide deep neural networks with a sufficient number of reliable labels, we can effect efficient training without too many labels that could be also costly to acquire if they were perfect. So the whole issue is now how, starting from noisy labels, we can get better labels, even with unreliable settings. And here is my mathematical setting that will allow me to come up with crowdsourced labeling approaches. N will denote the number of data points, the number of feature vectors. Xn, Yn, the input-output data. And suppose that I'm talking about the supervised classification setting, so I have K classes. I also have M annotators. These annotators here, or weak learners or unreliable learners, observe the X's, maybe a subset of the X's as well. And with all their labels, with all their observed feature vectors, they come up with the Y check, okay? Sub n for the nth feature vector, sup m for the m annotator. So the goal is simply stated as follows. I give you Y checks, all the noisy labels that I can have, find the Y hat, which is again, hopefully a better estimate of any of the Y checks for the nth datum, okay? So the question is to ask, how do you assess reliable annotators? Which are reliable? And once you have that, how do you optimally fuse? You need a framework, you need a criterion to come up with. But one thing that we should bear in mind is that this is, and crowdsourcing pertains to the fusion, the label estimate of the fusion center. And this is noisy, unsupervised, in the sense that we have Y checks, but the fusion center does not have access to X. In that sense, we are unsupervised. Okay. What are the approaches available? The simplest one is majority voting, right? So basically, you get 11, let's say, responses about one datum. 6 of them say it's a cat. 5 of them, they say it's a dog. Okay, you vote cat, right? That's a majority vote. Simple, but it does not take into account the reliability of the annotator. So something more sophisticated is well motivated. Now, there are model-based approaches, and I'm going to outline the one that is relying on the EM that offers at least local optimality, and Bayesian counterparts which view the unknowns as being random, and reliable one-parameter reliability models that are not as expressive but can be helpful in certain settings. And the novel part that we introduced as a group pertains to smart initializations of the EM that will aim at global optimality, okay? So, crowdsourcing 101. How do we go about labeling independent annotator responses? As I said, this data model is available. We assume that their IID drawn from a measure, from a distribution. And the data, I remind you, are white checks, which you can, for brevity in notation, you can collect in white check metrics. Columns are per annotator, and rows are the number of basically feature vectors. So what does map clustering, or I'm sorry, classification amounts to? You select that particular K, the class, that has the largest conditional probability of yn for any n feature vector, given the measurements. And if you basically use Bayes' rule, you can reverse the conditioning, and you condition on ground truth labels given all the possible yn sup 1 for the label of annotator 1 to come to be K1, one of the K classes, and y check and m to be Km. So this is the prior, the probability of yn to be K. As usual, we will, the usual assumption, not although Panos will allude to ways of bypassing it, is when you are given the ground truth label, the responses of the different annotators will be assumed independent. If you reflect on that, this amounts to saying, for example, that the y check is the true y plus noise that is independent from annotator to annotator. That's not too bad of an assumption. Although, if you start introducing graphs, then you can play with dependencies and make your life easier. But for now, let us assume that this holds. And that is useful because it makes the conditional on ground truth label probability of the labels of annotators to be factorable. And as usual, log is monotonic. We take the log of these products and we get the map rule to read as the log of the prior and the log of the conditional y check given y, that from now on I will call the confusion probabilities. So what's the probability of y check to make an error, although the truth is K? But going back to basics, Bayes' rule can afford performance analysis, and a performance bound under this assumption asserts that we have constants alpha and beta, for which the error probability of the map classifier accepts a bound that decays exponentially as the number of annotators increases. So basically, we can send the error down to 0. So we have a map classifier, which is optimal, and we have an assessment through the performance bound. So how bad I left the elephant in the room untouched. I talked to you about the prior. What's the probability of yn to be K? And I talked to you about a confusion matrix, a confusion probability of y check to be K prime, given that the true is yk. And I will group all of them to a matrix H that is K by K, with superscript M corresponding to each annotator. And that will exactly capture the reliability of the annotators. So the problem starts becoming interesting. Okay, the map rule is feasible and nice and easy, but provided that you know the prior probabilities and provided that you know these H's, which are the reliabilities. Okay. Now, what are the model parameters? I said once more, all the prior probabilities and the confusion matrices. And all of these have to be estimated from the noisy annotator responses. The first question you're going to say, is this possible? And is it unique? That's the identifiability question. And if we make an assumption that most annotators are better than random, which means that the probability of the y check n to be K that's the probability of correct decision, is greater than all other k primes, that satisfies this assumption too. And if this is correct, then it turns out that the model is identifiable. So you can find the h's and the pi's. If this is not true, then lower your expectations. You go to a less expressive model, and what you do is, instead of having every entry of this k by k matrix, which is symmetric, to be unknown, you basically adopt a one parameter confusion matrix, which has a diagonal that is alpha m. You see this has a minus sign, and the same has a plus. So when you postulate a model for the confusion matrix, which is a diagonal, with the diagonal entry being this alpha m constants, then your life becomes easier. So the identifiability conditions are not as stringent, these are not stringent anyways, but you can even accommodate cases where the assumption 2 can be violated, okay? So I talked about expectation maximization, and this is exactly where it comes into picture. We're observing these y-check variables, but we would love to have observed the latent variables, which are the true ground truth labels. And we have identified a bunch of parameters, the priors and the confusion probability entries, that would make my map classifier happy and ready to give me the optimal label. So what happens, the EM maximizes this log of the probability of y-check, parameterized by theta. And if you marginalize over the y, then this is the same as the joint of the ground truth label and the y-check. But obviously this is Gaussian. We don't know this, non-Gaussian, and we don't know it. So what EM does, picks up a tractable surrogate, PDF, Q, and you maximize the expected lower bound using a two-step iteration. The expected value of this log of this joint PDF is written like the log of the y-check, which is what we are after, minus the KL divergence. And if the surrogate Q comes close to this conditional, then this becomes 0, and you're your bound is tight. So without any further elaboration, since I assume the audience is mostly familiar with the EM, so the two steps that are involved, in the first step, you estimate the latent variables y when you are given the ith iterates of the unknown and also the y checks. And in the second one, you maximize the same. And this time you update the parameters, although you are given the latent variables that you estimated from the step S1. This amounts to a majorization minimization approach, and a sequence of non-decreasing likelihoods ensures monotonicity of it, ensures that you have convergence at least to a stationary point, which is the global optimum if you are sufficiently close. Now, if you want to the specifics of EM for crowdsourcing, I remind you that our unknowns are the priors and the confusion probabilities that they are trying to maximize this PDF. So the initialization that I will elaborate later, how a good initialization can come up, is starting with a theta 0, hopefully close. And then in the first step, you estimate the Q, which is I remind you, the surrogate PDF, using y checks and the previous H's from the previous iteration I. You go to estimate Q at I plus 1. And in the M step, you are updating the thetas, which you do in closed form once the Q's are given. All right, the details can be tracked if you follow the slides or the corresponding papers that I'm citing here. But let us reflect on the key question. How can I come up with a reliable initial estimate so that I can collect the benefits of EM? Well, the equivalent question is, can you give me an estimate of these H's and Pi's without the EM? And the answer is yes, through moment matching, a standard technique in statistical signal processing for initialization. To this end, it is useful to vectorize the annotator responses, white checks, with a one-hot encoding, which amounts to having a standardized EK prime if the YNM, the check, this is the label estimate, is K prime, then you put N1 in the K prime entry of this canonical vector E. And then if you follow this definition, then the expected value of a finite alphabet vector is basically this value, EK prime, times the probability of having K prime, given that the truth is YK. And this amounts to a vector HKM, that's how we define HKM. Now, if you go to the Y check and you take the expected value, Y check NM, then this amounts to the conditional expectation times the prior. So basically, what you see on the left-hand side are the averages, the first order moment, the ensemble of the label of the annotators expressed in terms of the product of H's, the confusion metrics, and the prior. And if you want to go one order up, you look at the covariance or the correlation, rather, in this case, of the annotator labels. And then you have a quadratic form with the diagonal of pi in the diagonal. And likewise, you can proceed and look at tensors where you have 3 copies of the annotator responses, and correspondingly, you can have a parafact tensor with unknowns, the H's and the Pi's. And all I've told you is that if you could estimate the third order moments, then the first, the second, and the third order moments of the annotator responses, you can recover the unknown parameters from the moments. But now we are in a relatively easy setting. How do we typically estimate ensembles? By averaging. So if you go across data and you take the average of the annotator responses, then you can have mu hat, which is basically the estimate of the ensemble mean. Likewise, sample covariance and estimates ensembles, and third order is estimate the third order correlations. I remind you that each one of them, the M here corresponds to the dimension, how many non-redundant elements you have. The M given 2, choose 2, and M choose 3. This is the number of equations you have, basically. And that should be greater than the number of K. And it turns out that third order moments ensure identifiability of this. And the moment matching obviously scales to large data sets because you just have to do sample averaging, additions. And how about performance? Well-known results. There are certain conditions that basically ensure mixing conditions that the sample estimates converge as n grows to the ensembles, and therefore the distance between the solution sets and the optimum with infinite data, the ensembles, and the sample go to 0 almost surely. And at this point, let me also point out some references from by Ibrahim and Xiaofu is the advisor and collaborators that demonstrate how to bypass higher order moments that are known to be having high variance by leveraging different constraints. For example, the fact that the things that you are looking for are probabilities, right? And they are non-negative. So it's that first two plus non-negative constraints can be used to unveil the known H's and P. One example before numerical test before I pass it on to Panos. We generated data, 1,000 of them, 5 classes, and selected randomly these confusion probabilities from a distribution that K follows HKM. And the figure here that plots classification error, basically the smaller the better, versus M, the number of annotators, with exponential decrease, confirmed as well. This figure compares the oracle, where these H's are precisely known in the synthetic example, with the majority voting, which is basically this dashed yellow, and this the worst, and the moment matching with also the blue here that comes close to the bound, which is the oracle. So what we see here, that if you initialize the EM with the moment matching, you can come extremely close to the oracle, and you outperform clearly the EM alone and the majority voting. So this is the point where I have to pass it on to Panos, who is going to talk about crowdsourcing with graph data, and we'll start justifying the G in the Degas. But I will close it by saying that crowdsourcing can be cast as a noisy, unsupervised learning task, and tools from statistical signal processing and formulations with map and tools for figuring out what is unknown in the map classifier can be utilized even with non-graph data, of course, under the assumption of conditional independence given the ground truth labels. Pano?
Thank you very much. I'm gonna, I can't share my screen yet.
What I stopped sharing. I stop.
Okay.
Yes, then you can stop, Jorgo, and then Panos can. I give him also, let's see, I have to give him the rights. Let's see. To find you in the long list here, by yeah. Yeah, so now you should be able to share.
All right. So you should be able to see my screen and the laser pointer.
Yes, we got it.
All right. So there's a small discrepancy between the slides here. I removed something last night, but so far, Professor Giannakis has been talking about how can we do crowdsourcing when we have IID data. But as you might already know, in many cases, there are dependencies between our data that we might want to exploit that might help us in a classification or any regression task. And in many cases, these dependencies may be known, or these correlations may be known, or they can be estimated easily from the data features themselves. And an example of the dependencies being known are basically, for example, time data, time series data. Basically, you're at time step t, you are dependent at time step t-1, and so on and so forth. But for the next few slides, we're going to assume that basically our data lie in a graph, calligraphic G, with vertex set V, where each of our vertices or nodes correspond to one of our data. And we have n vertices because we have n data. And the edges that capture correlations and connect the different nodes together. Examples of data that lie in a graph involve citation networks, brain networks, social networks, or power networks. You probably know more examples. And also, as we will show later, in some cases, you might have constraints that might help you with your machine learning task, and this can also be captured by graphs. Now, what we want to show here is how can we use this graph knowledge to help us in the crowdsourcing task. And essentially what we will do is we will say that we will look at it from a top level point of view, and we will say that all the dependencies are captured by the labels themselves, not by the data features, but by the labels, and we will encode the graph in the marginal probability of the labels. And we will also further assume that assumptions 1, conditional independence of annotators, and the fact that they are better than random also hold to make things easier for us. So now let's attempt to extend the prior probabilistic model to graph data. So as we said, we will encode the dependencies in the marginal PMF of the labels, this probability of the vector y. And we will do so but by what is known as a Markov random field. Basically, what the Markov random field says is that each node in my graph, the probability of each node in my graph depends only on its neighbors. So if I have here the conditional probability of label yn given all other labels, this should be equal to the probability of label yn given only its neighbors in the graph. Then the Hammersley-Clifford theorem asserts that since we have a Markov random field, this probability is essentially a Gibbs distribution, and we can write it in this form, where here for each of our data points, we have a term that, let's say, captures the prior, as we had before, plus some that are known as some things that are known as click potentials that capture the correlations between our different data points. So for each n, these VNs capture the connection between its neighbors in the graph. Now, the problem with this Gibbs distribution is that this normalization constant here is intractable, especially as the number of data grows. So the bigger my y vector is, the harder this normalization constant, computing this normalization constant becomes. Nevertheless, in this work, we define the click potentials in this way, where Wn prime is just a positive scalar. And this is the indicator that yn and yn prime have the same label. And the reason we do this is we want to promote the same label for data that are connected in the graph. You can think of it as a smoothness over the graph, essentially. Now, to complete the probabilistic model, we also have to assume that annotator responses for each n, for each datum, depend only on the yn. So let's say that our annotators only, to give a response to yn, they only observe yn itself. So the dependencies are only, as we said, captured in the labels. And then if we assume, if we inherit assumption 1, the joint PDF has this form again, where we have the product of the confusion matrices and the Gibbs distribution here. And this is essentially a hidden Markov random field, where for each hidden node, you have multiple outputs for each of our annotators. Now, we would like to do map label estimation as before, but the presence of this normalization constant makes this problem intractable. However, in this work we have done, we approximated this using expectation maximization as before, but the problem was that the E step didn't have a closed form solution. So in order to be able to approximate it, we used a method called iterated conditional modes. Now, there are other methods that you can use, such as Gibbs sampling or mean field approximations, but in that work, we found that iterated conditional modes works pretty well. Now, in the interest of time, I'm not going to cover it, but I will show you some real data tests with our proposed method. So here we evaluated the proposed approach in terms of F-score. So F-score essentially gives us a measure of classification performance, and higher is generally better. And for these three datasets, which are citation networks, we had we had features for each of our data, and also the graph is provided with a dataset. So basically here we trained 10 classifiers using MATLAB and on the dataset features without knowledge of the graph. And then we deployed them on a testing set. And here, these are the properties of the datasets. And we compared here majority voting, the moment matching plus expectation maximization for IID data here. And these last two columns are the expectation maximization method that takes into account the graph cognizant EM. So here we see that if we initialize it with majority voting, we get the best results out of the bunch, but also with moment matching. But also if we initialize it with majority voting, we also get decent results, and most of the time we outperform the IID methods. And note here that these results are pretty good, considering that for this dataset we have 10 classes, and that for this dataset we have 3. We also evaluated the method on 2 crowdsourced datasets. Here, unfortunately, we didn't have a graph provided with a dataset, so we had to create one from the data features. So here we used the k nearest neighbors. And but here the annotators are essentially humans that are providing the answers, in contrast to this example where they are machine learning algorithms. So again, here we can see that incorporating graph knowledge improves your classification task. Next, I promised to talk about constraints. So constraints typically arise when we have access to additional domain information. So these constraints might be available labeled data. So we might have labels for a few of our datasets, of our data points, or we might have information about the physics of the problem or some domain experts. Now, the constraints that we will focus on here are so-called pairwise constraints or instance level constraints that basically connect 2 data points to each other. And the popular categories of these are the so-called must link and cannot link constraints. Now, these constraints are provided as tuples, basically telling us which data points we should connect. And the must link constraints tell us that data must belong to the same class, whereas the cannot link ones tell us that data must belong to different classes. And again, I can encode these in a graph, G, where again, the set of vertices are my data points, and the set of edges correspond to my constraints. And the weight of the edges tell me, for example, if I have a must link constraint, you might have a +1. If I have a cannot link, you have a -1. Here in these 2 figures, you can see 2 examples. So the solid lines are must link constraints, and the dashed line is a cannot link constraint. So here we see that if we incorporate these constraints, we get these 2 classes. Whereas if we had not known these constraints, we might have gotten different classes from this problem. And also, the bottom figure shows an image of Patras, and the colored boxes are the locations of the constraints. So if you have 2 green boxes, this is a must link constraint, but the green and the red form a cannot link constraint. And the black lines show the segmentation that resulted in this image using these available constraints. Now we can take these constraints and plug them into the probabilistic model for graphs that we had earlier. And in this work that we did here, we used variational inference instead of expectation maximization. However, it works pretty similarly. And again, we can see that using this graph information, this constraint information, improves our classification performance as long as we have good initialization. And the good thing is that you can show this both empirically, as we will show in the next slide, and analytically. So there is a theorem that shows that given a good initialization, you can improve your errors over time. Now, here we have real data tests for the constraint. So here we consider 4 crowdsourcing datasets, again, human annotators, and we compare majority voting the EM algorithm for IID data, variational base for IID data, and two methods that use constraints. Here, VBLC uses label constraints, so you have more information. For some data points, you know exactly the true label. And VBILC for instance level or pairwise constraints, the method I just described, basically using the graph. So what we see here is that in the top two figures, we have the F-score as we increase the number of constraints. And we see that the methods that don't use constraints, of course, have a straight line because they are not cognizant to the constraints. However, even if we use instance level or label constraints, we get very similar performance. But this is for only two classes. However, if we go to more than two classes, the label constraints contain more useful information, essentially. It's better to tell me that if a data point belongs to class 5 than telling me that two data points are the same class, essentially. But here we can see that even though we are using instance level constraints, which are slightly less powerful, let's say, we are still getting an improvement in classification performance. Now, of course, if you increase the number of pairwise constraints, you will get an increase in performance and potentially reach the performance of label constraints. However, with that, I will now go to the third part of the talk, which is some of the most recent work we have done. So we'll be changing gears a little bit, which is crowdsourcing. How can we cope with adversarial attacks in crowdsourcing? So in our model here, the adversaries may hide as annotators. So basically, we have adversaries that wish to decrease our classification performance or drain resources from our system that hide as annotators. So essentially, they give us to the Fusion Center wrong labels, or they manipulate the labels in some smart way. Now, the problem is that if they are successful, they might poison a data set. So they might give wrong labels to a data set that might be used for a downstream machine learning task. And this could yield bad results for the inference model that we're trying to train. Now, in this context, what we are trying to do is we're trying to figure out which are the worst possible adversarial attacks and how can we identify them and mitigate the effect of the adversaries, possibly by removing them from our data. Now, there have been some prior works on this. There is a spammer detection algorithm that modifies the expectation maximization algorithm for IID data during the label fusion stage, essentially. And also there are other algorithms under the simple one parameter model that allow for arbitrary adversaries. However, these adversaries shouldn't exceed more than 50% of the available annotators. In this context, what we showed is that we can do spammer and adversary under certain conditions, but I will not cover this in the interest of time. Under the more general David-Skin model that Professor Giannakis described earlier, and prior to the label fusion stage. So basically, essentially, we're using a moment-based approach again. Now, to do this, let's take a step back and look at our crowdsourcing model again. So essentially, our crowdsourcing model says that our annotators are conditionally independent. And if you look at the probabilities from an information theoretic point of view, this will look essentially like each annotator is an independent information-bearing channel. So an annotator receives the input, in this case, Y. It passes through the channel matrix, which is, in this case, the confusion matrix, and it provides us with an output. So this is basically a depiction of the annotator channel. Now, since I'm considering annotators as channels, I can benchmark their performance but by what is known as channel capacity, which is the maximum mutual information between the input and the output. and this is a non-negative quantity. But since our annotators are independent, the overall capacity is just the sum of the individual capacities. Now, if I were an adversary and I'm not allowed to communicate with anybody else, so I still have to be independent from everybody else, the worst thing I can possibly do if somebody can find out my channel, so if somebody can use the techniques we mentioned earlier to figure out what my parameters are, the worst thing I can do is basically set my capacity to 0. And setting my capacity to 0 essentially means that my output is completely unrelated to my input. So I am just a random number generator giving random numbers to the fusion center. And in that case, my confusion matrix will be this rank 1 matrix, where this S is a probability vector that is unrelated to my task. So for this, for the next slides, we consider two groups of annotators being present in our dataset: the spammers belonging in set S, which we have to remove because they provide us with no useful information. They're just draining resources. And the honest ones in calligraphic H that follow the David and Skin model, and they can give us useful information. Now, to show you why adversaries are bad, we have a toy dataset here, a synthetic one, where alpha is the percentage of annotators that are present as adversaries, and the rest are honest. And here we evaluate an Oracle classifier that knows everything. So this will cover all algorithms that can estimate the parameters of annotators and majority voting. And also we consider two types of adversaries: spammers, we just mentioned, that give us random responses, and what we call here malicious ones, that essentially their probability of giving us the wrong answer is greater than the probability of giving us the correct one. And in this figure, you see the accuracy as we increase the percentage of adversaries. So for majority voting, we see that the performance decreases fairly rapidly, and malicious annotators have a worse effect than spammers, but not by a much. However, notice here the Oracle, where for malicious annotators, the performance remains fairly stable. And that is because if I know that somebody is feeding me wrong answers, I can always flip them. However, if we have spammers, the performance drops significantly. And this is essentially due to the fact that spammers basically are as if I had less annotators. Hopefully, I convinced you that spammers are bad in this context. So now let's see how we can detect them. So if we have an annotator, any annotator, and another annotator M prime that is a spammer, then their cross covariance, indicated here, should be equal to 0. And in principle, I should be able to use this fact to flag spammers. However, due to noise generally, this won't be equal to 0. So we need a way to denoise these cross covariances. So it can be shown under the David and Skin model that for two different annotators, the cross covariance has this form, where this D is a positive semi-definite matrix of rank k-1. And notice here that the autocovariance has this form, which is significantly different than this. So if I gather all cross covariances, and notice that these are scalars, by the way, in a matrix, and use the fact that this is positive semi-definite and take the square root, we can show that this cross covariance between two different annotators is the inner product of two vectors, Vm and Vm prime, which vectors have this form, and these vectors are of dimension k times 1. And if I stack them in a matrix, then we can see that the cross covariance, the overall m times m cross covariance between all annotators is a low rank rank k plus a diagonal matrix. And there's a typo here, by the way. I apologize for that. But our idea here is that if we have a spammer where the confusion matrix is rank 1, then the corresponding V vector should be close to 0. So to take advantage of that, what we do is essentially we take the sample version of the cross covariance matrix and we use a low rank plus diagonal decomposition to figure out the V matrix. Now, one way to do it is using this simple convex program. So we say that our sample cross covariance is equal to a diagonal plus a low rank matrix, and we want to minimize the rank of the low rank matrix. So the nuclear norm promotes low rank solutions. And this omega is just a mask indicating whether two entries of the matrix are observed or not. And this happens because in crowdsourcing, different annotators might not label the same subsets of data. So in that case, you might not have any information between them. So after we recover matrix L from this convex program, we can use SVD to recover V, and we can then cluster the rows of V into two clusters using k-means, and we can identify the spammer cluster by figuring out the one that has the smallest average norm. Now, I'm going to skip this in the interest of time, but I can show you what our results were for real crowdsourcing data. So we took 3 data sets and we wanted to figure out if there were any spammers in them. And if they were spammers, if the algorithm we used figured out they were spammers, we removed them from the data set. And we denoted the algorithm as algorithm 1 here. So here we compare the accuracy for majority voting, the expectation maximization algorithm, and our spammer detection algorithm, followed by majority voting and expectation maximization. And the parentheses here indicate the number of annotators that we removed from the dataset. Now, in almost all cases, we see that we have an increase in classification accuracy after we remove annotators. In some cases, we don't have any significant increase, but still this is beneficial because we just don't have to compute the parameters for, in this case, 12 extra annotators. And in general, the bottom line here is that if we identify and remove spammers, we can potentially improve the performance of crowdsourcing. Now, what I didn't show is that we also have a method for adversaries that is, it has a similar spirit, but we don't have time to cover this. So with that, we reached the conclusions. So if you want to remember anything from this talk, is that you can use crowdsourcing to fuse decisions from possibly unreliable annotators or unreliable models. And one of the most popular models is the so-called David and Skin model that assumes that annotators are conditionally independent. And using the EM algorithm, you can find good parameter estimates. And if you use moment-based methods, you can initialize the EM algorithm to yield even better estimates. Another thing to take home is that we can adapt crowdsourcing to the cases of dependent data. So if we have a graph that tells us which data are correlated, we can use it and it will improve accuracy. Now, some of the current and future research we are working on is what happens if you have dependent annotators. So we saw what happens if you have a graph describing your data, but in many cases, your annotators won't be conditionally independent. So in that case, you possibly have to find a graph describing the relationships between them and use that to do label fusion. Also of interest is what happens if we have dynamic graphs. So basically our data are evolving over time, the correlations between our data. If you have colluding adversaries, again, this is related to the dependent annotators. And finally, we are also considering what happens if we have alternative forms of annotation. So our annotators are not giving us labels, but they might tell us that 2 data points belong in the same class, or they are giving us triplet relationships, that data point A looks more similar to data point B than data point C, or they just give us multiple instance type of annotations. So there are 20 positive instances in this bag of data. With that, I'd like to thank the organizers and thank all of you for your attention. We'll be happy to take any questions.
Thank you, Pano and Jorgo, for the nice presentation. Okay, so yeah, we go now to the questions part. I don't see anything yet in the chat, but if people want to ask a question, just unmute yourself and then go ahead. Maybe I can start by going back to this, so to the graph data. So so that doesn't yet model the dependency, right? They're still conditionally independent, you say, right? But
yes, the annotators are conditionally independent, but the data are not IID in this case.
Are the true labels?
Yeah.
And do you somehow see that back in some kind of so it's not that H has a kind of a structure of a graph, right? That the H matrix is sparse somehow, right? That's not the case, right? So do you, I mean, I just wonder where you see back like an adjacency matrix or something on the graph.
So
in the V, in the V somehow you see that, right? So
yes. So essentially the V here captures the connectivity of the graph essentially in the
prior,
the prior. So if you were to write this the EM algorithm in MATLAB, you will see that the adjacency shows up in matrix vector multiplications in order to do stuff in a fast way.
And otherwise, if it would be conditionally dependent, it also ends up in the H matrix, I guess, right? The adjacency somehow.
So in this work here, the adjacency won't show up in the H matrix because here we assume that annotators are giving us a response only for the label that they are looking at. So you can think of it as this is the label and the annotators are.
But it could be, let's say that you, let's say you're in a classroom and you look at your neighbors, right? And you also take into account what they are doing. And so in that case, right, I mean, that's what you say in the future work, I guess, right? So that you have conditionally dependent. And then, I mean, in that case, right, in that, I mean, I know that it doesn't show up here, but in that case, you also have the graph showing up in the H part, right?
Yeah,
I guess.
Exactly.
Yeah.
So you have to deal with it in the confusion matrix. Like you have to figure out a different model for the confusion matrix. And also figure out the graph in many cases, because you might not know it.
Yeah, so that was my second question. So here you have to, you can estimate this from the data, or here you assume that it's known, or in your simulations? So
for these data, in the simulations for some data sets, we assume that the graph was provided in the data set because it was a citation network. Right. But for these data sets, we used k-nearest neighbor. So we had the data features and we generated the graph. Okay. Right. Okay. So would it help there to use more sophisticated graph estimators, or it might not? Yeah. Potentially, yes. Yeah. I mean, the more information you can carry in the graph, the better you should be able to do. Right. Okay. Thank you for the great questions. Any other questions from the audience?
Good. Can I ask a question?
Yeah, sure.
Hi. Thanks, Yorgos and Panagiotis, for the nice talk. I
like your gray hair.
I have a question about the clique potential. I saw that you assume that you have pure homophily, and we know that graphs in general are not purely homophilic. So we have some degree of heterophily in the graphs in general. It could range from up to 30% sometimes. This is what we've measured in some of the graphs that we have used. Scora, for example, I think is 23%. So I was looking at this assumption, I was wondering whether this is something that has to be assumed in your work, or the work could be extended to heterophilic graphs.
Great question. So in general, we use this to make things easier. But if you notice here, the weight can depend essentially on the edge in the graph. So if we have information about how strongly correlated two nodes are, we can potentially use it in this way. We can incorporate it appropriately in this way. Of course, we can also use other types of click potentials, like more complicated functions that might be able to capture the dependency more accurately. And I would be very interested to find out what types of click potentials could work there. Yeah, sorry.
So this could be modeled as a transition matrix, basically from class 1 to 2. We have this potential, meaning that we have two nodes being connected if they belong to the same class K with probability, I don't know, some value. And then we may have also connection between two nodes that belong to different classes with different probabilities. You have basically a transition probability going from one class to another. That would generalize basically this assumption that you have here. But I think the rest of the work could be valid, I think, for a more general assumption, I think.
Yeah, that's a great suggestion. Yeah, I would like to look into it more. Like now that you mentioned, I actually wrote that down.
Okay.
Yeah.
Thank you.
Thank you very much.
Thank you, Munir.
Other questions?
For those of you that may want to, may have other questions later on, feel free to send us emails. Both of us have websites and our emails are there.
Yes, and if the presenters agree, we can also put the PDF of the slides on the DIGA website. So for sure the talk will be there, and then we can also put the slides.
Sounds good. We'll send you.
Okay, so thanks a lot. I don't see any more questions. So great that you were here to give this talk on this kind of interesting field where graphs can come into the picture and give us some new perspectives on this. So that's really nice. Okay, thanks.
Thank you.
Yeah.
Thank you.
For having us.
Thank you.
Thank you.
In 2 weeks, we will be back. So stay tuned for more in this webinar series. So see you all. Bye.
See you.
Bye.
Bye. Thanks.
Bye.